Good afternoon, everyone. Thanks for joining this third webinar. Today's topic is entity resolution, and Bianca and Radu will be your host for the day. So if you have any questions, feel free to ask them in the questions pane of the GoToWebinar tool. I will gather them and then share them with our host at the end of the session. Bianca and Radu, there you go.
Thanks. Hi, everyone. So welcome to the third webinar, the Unit8 Talks. All right. Okay. So my name is Bianca. I'm a data scientist. I've been with Unit8 for about 8 months, and I'm joined by my colleague Radu today.
So I'm Radu. I'm a big data engineer. I've been with Unit8 for almost a year and a half.
So today's webinar is on the topic of entity resolution. So today we're going to walk through a little bit of an introduction to entity resolution. We're going to go through a few use cases. We're going to delve a little bit into typical steps of an entity resolution pipeline, and then move on to a live coding example. So let's start with why do we need entity resolution? Here at Unit8, we handle a lot of data for our customers, and a lot of data often implies data quality issues. These two things kind of come hand in hand. One of the ways that we handle that at Unit8 is using entity resolution. So what is entity resolution exactly? It is about determining whether records from a different data source represent, in fact, the same entity. So we could be dealing with figuring out if two people are the same person, or let's say if two books are the same book. Entity resolution can actually be found in plain sight around us, even though we might not really be aware of it. So let's look at some examples. When you go on Amazon and you want to buy something, you can tell that there's a lot of different distributors where you could possibly be getting what you're buying. So Amazon might ask themselves, how do you tell the total stock of a certain product given all our different distributors? And the answer to that would be using entity resolution. On Facebook, you know that you're not really allowed to have two accounts for the same person. So they need to have a way to figure out if I'm trying to make two accounts for myself. And the way to do that is using entity resolution. If you want to expand it a little bit, we can look into a bigger domain. We can look at insurance and finance. And companies in this industry will have a big issue of trying to prevent people from committing fraud, trying to prevent people from having, let's say, multiple insurance policies, from taking multiple loans and things like that. And this is usually done with the help of entity resolution. But in order to better understand why we need this and how does it actually work, let's imagine a scenario and delve a little bit into details. So let's say we have this big bookstore. It's called Books with a Z, and they decide to acquire a smaller bookcase called Books. And they want together to make one big bookstore. But the thing is, right now, they're storing their stock of books in different data management systems using different way to access it and process it. And let's say we have some books here, we have some books in the books data warehouse, and we want to figure out what books do these have in common? Because now they're going to be one big bookstore. They need to know what books they both have, what books they have on one side, and put them all together in the same place. So we can already see here, a few of them look to be the same. So what we're trying to obtain is this. We have a new big bookstore, and they know in a centralized way which is all the stock they have together. So essentially, this is the question we're trying to answer. Is this the same book? And that is called entity resolution. You might find it under a variety of other names, such as record linking, data matching, or deduplication, but in essence, it's the same thing. So you might ask yourself, what could possibly go wrong with that? I mean, look at them, they look the same. A few things come to mind. Let's say that Books with a Z stores all the information about books in a database, while Books, the smaller bookstore, goes for a little bit of a more old school approach and decides to store everything in a big old spreadsheet. That's one problem, but then here comes another problem. Let's say that in the database, we have the schema looking like this. We have the title, the author separately, and the stock. Notice that here it says 20. Let's say that in this case, it's actually thousands of pieces. On the other hand, we might have this schema, which is the title concatenated with the author, all put together, and it's directly in number of pieces. That could be a little bit problematic already. Then there's another even bigger problem. Look at these 6 books. In order to figure out if these books, which books are the same, we would need to compare them to each other. And these are all the pairs we would need to compare in the case of just 6 books. The number would add up to a combination of 6 choose 2, which is 15 different pairwise comparisons for only 6 books. Imagine how that really scales for millions of books. It would be very easy for a machine to run into trouble memory-wise. So now let's look a little bit into how does entity resolution tackle that and other problems. So we're going to look a little bit into start with this diagram. We have the data sources, we have aggregation, followed by preprocessing, by blocking, featurizing, classifying, clusters. It's all a big abstract diagram now. And you might find this in different ways in different sources. You might find different namings or some phases put together into one. But in essence, those are kind of the steps that are usually found in an entity resolution pipeline. We're going to go a little bit more into detail. So first one up is aggregation. Continuing with our bookstore example, let's imagine that we have these 3 databases and we have different books in every one of them. And the goal of this phase is to obtain a centralized version of all these books, one table where we can access all these sources and under the same schema, but we'll go a little bit more into detail of that in the live coding part. So now we have all our books from all the different databases, spreadsheets, whatever, in one place. Going to move on to preprocessing, which in essence is the stage where we're going to clean our data. And by cleaning, I mean we're going to have things like dates. Dates, you all know, we can find them in a variety of formats. And we need to clean them and bring them in the same format. We could have special characters. One example here would be emojis are pretty big nowadays. What do you do with them? You could just remove them, for example. Transliterations. Here we have a German name, Peter Müller, and we might want to not have non-ASCII characters. So let's say we can turn it to Peter Müller. But you might also want to say Peter Müller with a UE because that's closer to the actual phonetics of it in the actual interpretation. And this is still quite easy example. We could have entirely different alphabets within the same table. Then we could look into formats a little bit. We can have 10K, but we can't really use that for anything, can we? So maybe we'll need to turn it into an actual number. Finally, we can also take a look at the casing, for example, which could be a little bit all over the place. So we'd have to bring it into the same format, maybe even sort our words, depending to what you need. So the goal of this is that after this phase, we have our centralized table. And now, furthermore, it's all interpretable in the same way, which is very important for an entity resolution pipeline. So now that we have this view, what are we going to do with it? We're going to move on to the blocking phase. In this phase, we're going to find candidate pairs. What we mean by candidate pairs is that if we imagine we have these 4 books in here, we're trying to look at which of those books are worth comparing to each other. That's exactly what blocking is. So let's imagine for a second that we are trying to block by author. What does that mean in our case is that we will consider as candidates books written by the same author. So basically what we're saying that we have all these books, but we think that it's only worth to try and compare those which have the same author. So in our case, we can see we have 3 books written by this guy, Bob Ross. So we're going to have to try to compare them to each other. So we have this pair, we have a second pair here, and the third one. At this point, it becomes apparent why blocking is really important. And it's exactly because of this. We have this book written by John, but because it doesn't really fall into what our blocking strategy is, we will not compare it to any of the books written by Bob Ross, which is great because that means less work to do. That is the entire essence of blocking. In this case, for example, we reduced the pairwise comparisons by 50%, which is a significant improvement. It scales much better than what the graph we were looking at earlier. So now that we have our candidates, we need to start looking at them and figuring out how similar are they really, these pairs. So this is happening in the featurizing phase, where we create features to measure the similarity of the pairs. You can do this for a variety of different types of strings, dates, everything. But for the purpose of this exercise, let's look a little bit into two simple string similarity metrics. We categorize them in two ways. So we can look at token-based, and an example of very common metric used here is the Jacquard similarity, which is defined as the intersection divided by the union of a sample set. And this is pretty much a fancy way of saying it checks which words are in common between two strings. We have another category that could be edit distance based. So here a pretty common metric is the Levenshtein distance, which really means how many deletions, insertions, substitutions are required to transform a string into another. There are a lot of multiple other metrics in the same categories, and there's also entirely new categories. For example, you could use phonetic algorithms to also take a look at your strings to see if do two strings kind of sound the same maybe? But for the purpose of this example, let's try and focus on these two metrics and look a little bit into what exactly do they mean and how do they work. So let's say we have this book called Beginner's Art, and then we have this other book called Art for Beginners. And we try to compute those two distances that I was just talking about. Our Levenshtein distance will be 12. So that means that we would need to insert, delete, and substitute 12 different characters to turn Beginner's Art into Art for Beginners, which is a pretty big distance. However, the Jacquard similarity tells a pretty different story. It's actually a much better score, because out of all the 3 available tokens in here, 2 are in common in both. Similarly, we could have another book called Beginner's Arts, but a little bit misspelled. And here we have a Levenshtein distance of 2, which is pretty small because, as you can tell, it's just like a few typos there that you can adjust. But the Jacquard similarity tells something completely different. It says they're not similar at all because none of the tokens are in common. So what I'm trying to get to with this is that featurizing is really, really important. At this stage, you kind of define the outcome of your pipeline. You need to really know your data to really understand why you're making a pipeline. What are you looking for? Do you want the typos to be captured? Do you want just words to be the same? Which one of those would you prefer? So now we finally have our features. We're going to use those for classifying. This is the stage where we actually say, are these two pairs the same? And we can do that in a couple of ways. We're going to look at 3 architectures today for that. We could get our candidate pairs and give them a rule. And then we use that rule to decide if that was a match or not. And we only use that rule. So we can say we'd like books which have the identical title and identical author match. If that doesn't work, then that's a clear no match. Instead of that, we could use a model-based approach as well, where instead of the rule in the middle, you have a model, which pretty much does the same thing, match or no match. We could also have a hybrid architecture, where let's say we have our candidate pairs, we do the rule-based approach, we decide to yes or no, but if it's a no, let's say we don't want to just discard it, so we try to put it through a model and see what does the model say as well. Does the model also say it's a no? Or maybe it could be yes. You could also put them the other way around or create different architectures, but that's one example. For the purpose of this exercise, let's try a rule-based approach with the books that we were looking at before. So we have our art for beginners, beginner's art, and beginner's art, but misspelled. And we've computed our 2 features earlier. We've computed our Levenshtein distance and our Jacquard similarity. And here are a couple of options that we could have using those. We could say we want a high Jacquard index. And what that means is that we have a lot of words in common. We could also aim for a low Levenshtein distance, which means we'll tolerate small typos or small changes, and that's it. Or we could say we're happy with either of them. Like if one of them happens, we're fine with that. Or we could say we really, really want both to happen. And we get completely different outputs according to what rule we decide to use. If we go for a high Jaccard index, for example, we'll only get one pair matched. Low Levenstein, same. If we're fine with either, we'll get all of them. And if we want both of them, we'll get no matches. At this point, that's really up to you. There's a lot of trial and error. And again, it's a lot of knowing what you want to get out of your entity resolution pipeline. And finally, we move on to the light at the end of the tunnel, the clusters. After we finally classified, we'll be able to get a view of exactly what we were looking at the beginning, the goal of the newly formed books and books, where they know exactly how many books they have from everywhere and how are they grouped together in clusters. So this all was a little bit abstract. So let's see how that actually looks in practice with a coding demo from my colleague Radu.
All right. So as Bianca mentioned, there are a couple of scenarios. It might be Amazon or it might be Facebook trying to find out, let's say duplicate books. And you might think, okay, that's cool to know, but maybe not so critical information. Well, let's take another look at a fourth example in this case, which is rigged voting. So let's say you are, one person, they want to go to vote. You use your ID, you cast the vote, all good. But there might be someone else, and this someone has more than one ID, which is perfectly valid. It might be, for example, multiple nationalities. And they go to vote with one of them, it all goes fine, and then they take their other ID and they vote again, and again it's fine. But this doesn't seem really right. So it might be okay now if it's just one person. But what if you have more people? If you have a lot of people doing this, it might be completely changing the outcome of an election. And this, for example, in Switzerland, has been an article mentioning that there are over 25% of people that have multiple passports because of multiple nationalities. So it's a perfectly realistic example. So let's take a small example. We want to find out, who is trying to use multiple IDs. So taking a quick example. Sorry for that. So we want to use a notebook, some two small data sets. I want to, walk you through kind of the steps we talked about and see, what are the common scenarios, maybe the gotcha moments. And we're going to use pandas for a quick exploration. We read two data sets. And arguably the most important step is to see how the data looks like, really understand what you have in the beginning. So if we take the first source, you can, what do you notice here? You can look at the nationality. You might notice there's some missing data, might be written in multiple ways, or you could look at the address. It might seem kind of all over the place, some street numbers, some cities or not. And you might also have the first hint of what ER could be useful for. You can see two Joseph Miller here. Now, with this said, we also care a lot about the types. So for pandas, it's going to show as objects, which means it's most likely strings. Then if you look at the second data source, we can see that we have, again, kind of similar columns. We have names, we have birth date. Again, we see a country, again, with some multiple formats, some missing data. Okay, well, this being said, let's try and continue the process. First of all, we want to put everything into one place. So for that, we need a common schema. And for this, we decide to use the first and last name, date of birth, address. And you might notice that here we use nationality, which if you look at the second data source, it just says country. Well, this is exactly the kind of information which you get by discussing with business. So you really need to figure out what each column represents in the data. In this case, we know it's the country of nationality, not domicile or something else. So we're going to use these 5 columns. We also notice that there was a phone, which was completely null, so I guess useless. Let's just remove that. And applying this to the sources, we get data which looks like this. So we can already see we have the same columns. The types at this point are also the same. They're all strings. Well, if you look carefully, you see a date of birth. So this is where it's not just a string, it represents a date. So let's do that and convert it to a data type. And since, if you notice, per data source, there's a different format for it, we're going to apply it per data source. So for example, for the first one, we convert it to a date type in pandas. And you notice here, that's true, it's a date time. And we apply the same thing for the second data source. Now that we have the same column names, the same types, let's just convert it into one single data set. And with some small boilerplate for some pretty printing, it will look like this. We keep track of from which source each row comes. And we can notice, the two data sets in one place with a good schema. Now, if you look at the data, of course, you might notice still the things we saw in the beginning. Some missing rows, some null values, address still looks messy. Let's clean that up. So this is our pre-processing step. First, we want to remove the null spaces. So for that, we use a simple reg expression and looks like this. Then if you look at nationality, we really want to have the same format. We don't want Germany and the full name, then ISO2, ISO3. Let's keep all of that in ISO2. And for that, we use the PyCountry library, which has a really neat utility function, which lets us do exactly that. So as you can notice here, everything is converted into ISO2 format for the nationality. Then a next step, I kept mentioning the address is messy. So let's try and clean that up. First of all, you might notice a recurring 5-digit pattern. Well, in this case, we are using the German style of writing no Java today. A different style of formatting the postcode in an address. So that seems like it could be useful information. We see it also recurring in the small example. So let's try and extract it out as a different column. All of this code does exactly that. We now have a separate column, postcode, and which was extracted from the address, so it's no longer here. Now, a last step, we can look at the actual characters used. So you might notice the umlaut, for example, in Müller. You might notice that there's some different casings. Let's try and convert that to just one structure. And for that, we use, well, in this case, a simple mapping between the German characters to more phonetically relevant characters. And of course, you can extend this if you have other languages like French or etc. And at the same time, we lowercase everything just so it's the same. You could uppercase as well, it doesn't matter. So at this point, this is kind of the clean data. So you can notice it looks much better than before, at least I think so. So I think it's time for the more interesting parts of the entity resolution. So first of all, we want to block. So find candidate pairs. For this, we use the record linkage library, which has a lot of utils to do it really neatly. And the first step is, of course, we need to pick how are we going to block things. And we decide in this case, I think the last name and the date of birth, or the last name and the postcode should be the same for them to be potentially a match. So we define them as seen here. And then with, again, some boilerplate just for more pretty printing, we can see how this blocking turns out to be. So as highlighted, you have the different sources. You can see, for example, in the first row, it's coming from the same source. You remember that Joseph Müller situation at the beginning. And this was blocked because they have the same postcode and the same last name. So this was one of our rules. Another rule, you can see it in the second row. This was based on the date of birth and the same last name, which looks really good. Like this are good potential matches. But then, of course, you have two other rows, which are Katharina Müller and Joseph Müller. They're potentially good, so you want to capture this kind of information. But for us, at least now seeing the data, it's pretty clear they're not the same person. But nevertheless, this is exactly the point of blocking, just keeping possible matches. And to see a number, why this is important, let's look at how many matches there could have been, how many potential candidates, if we computed all of them. And it would have been 28. Now we only have 4 rows, so this is a drastic improvement on the things we keep as candidate pairs. And this was, of course, the whole point of blocking. Now, more towards the next steps is figuring out how to actually compare, how to conclude that these candidate pairs actually represent the same entity. So we call this featurizing. We first want to really compute some features. At this point, we no longer care about just the last name. We want to look at the full name and not be so strict about it. Let's compute a string similarity metric. In this case, we use Levenstein, and we choose a threshold of 0.85, which means if they're fairly similar, this whole row is going to output that it's a feature of 1. Otherwise, it would be a 0. Then we don't use just this, of course. We also look again at the date of birth and the postcode. And again, if they're exactly the same, it's going to be a 1, if not a 0. So applying these things onto the previous candidate pairs, we now have these 4 rows. So you can see again that Joseph with an F and Joseph with a PH, they have a feature of 1, so they are similar enough for this feature. And then you might notice, case when this is not true with Catherine and Joseph, or the same, same postcode, same date of birth. But now that we have this, okay, how do we really conclude? Are they the same or not? So for this, we define some rules. You'll notice it's pretty similar to blocking. Instead of using the last name, we now use the Levenstein of the full name. So if that's true, and also the same date of birth, or if the name and the same postcode, then yes, we say that this is a correct match. And these are the 2 rows remaining. So essentially at this point, we concluded that these pairs are representing the same entity. Now, okay, this is just 2 pairs. Might be still a bit abstract. So let's first extract the clusters and then also visualize how this looks like. For the graphing, we're going to use networks, another cool Python library, which lets us just put in the edges we have, the nodes, and then use a function of connected components, which is going to take those edges and those nodes and tell us which of them are connected into one cluster. So applying this, we can see at this point it's just a list. We can see that there are 3 entities together, which represent 2 from before, and some other were singleton clusters. But to actually visualize it, let's use matplotlib, and let's plot with some random colors. So you notice that those 3 entities I mentioned, they are one cluster, same color, and all of the others are of different colors because they're treated as singletons. Now, I hope this gave you an idea of how you could quickly apply it. In this case, just a notebook, some test data, how you can quickly apply all of the steps, and you can conclude, find clusters. But if you paid attention, that's always crazy. There were some cases where maybe it wasn't that correct approach. So if we look at what was matched, we can see there were these 2 entries. So we have a Joseph Müller in both cases. They're not exactly written the same. They have clearly a different date of birth. The address, it's kind of similar, but if you have just the street, it's a long street. There might be realistically more Joseph Müllers on that street. Nationality is also different. So you might ask yourself, was this actually the correct approach? Were the rules good enough? Was blocking successful? Then if you remember, we also had a J Müller. Now again, it might look similar, but there was the same date of birth with one of the entries, but there was no really other data to conclude. And we didn't even block it, just because it was typed differently last name. So what I was trying to say with these kind of examples is it's tricky. So in conclusion, we have the right implementation really depends on what data you have, really depends on the context, what data means, and the quality itself is critical. So if you have messy data, it's really hard to extract anything useful. And for this example, the clusters. And lastly, there are always exceptions. So like the J Müller, there's always something, some record, some data that is not going to apply to any of the rules you decided so far. And you will always need to iterate and iterate to accomplish as much as possible. And I think that ends this part. So we have time for questions. Please go ahead.
So thank you, Bianca. Thank you, Radu. So we've received a couple questions from the audience. I'll share them with you. After that, if you in the audience have further questions, please feel free to raise your hand and we can pass you the mic to ask questions. So no question about Java update, but first, how would you assess the quality of the data you use before running into the whole process?
Answer that.
Oh, go ahead.
So to assess the quality, it's kind of trial and error. So you really need to look into it yourself. You really need to see, what you have, what data types you have, what kind of format. It's really no clear concept. Even if you have, for example, business classifying these tables, to represent people, you might actually find other things as well, or it might, go all over the place. It's trial and error, I think, in a few words.
Okay, thank you. And maybe slightly related in thinking, how would you come up with the appropriate pre-processing steps, especially if you have tons of data to scroll through?
I think that's indeed quite connected to the previous answer. There's always a lot of resources about different checklists, different things you should always check for, like null values, appropriate formats, things like that. But it's a bunch of all of these things that are mandatory to check and all of those things that you're trying to achieve. So you try to think about how do you pre-process the data, having a goal in mind. You need to know what you're trying to get to, and then you define what you need to do to get there in the nicest way, I guess.
Okay, and one final question. How do you verify the output clusters as being correct?
So I think we've tried multiple times to emphasize what a trial and error process entity resolution is. But I think one thing that you could do is, since you are designing this with a goal in mind, you can take a bit of data, try to sort of label it, to figure out how do you actually would like it to look, and then try to put it through the pipeline and see what it outputs, if that's what you're expecting. And this is a good way to sort of figure out what do you need to reiterate on and what you should change and whether the performance is what you expect it to be.
Thanks. So I think we can remember that it's a big trial and error process to get through there with good results. We haven't any other questions, so perhaps you could tease us a bit for the next webinar.
Oh, of course.
Sure. So first of all, thank you all for joining today. It was fun for us. Hope for you too. And please join us on our next webinar on June 25th, that Thursday at 1 p.m., where Marcin and Tomek will talk about improving the overall equipment efficiency with advanced analytics and AI. We hope to see you all there.
Well, thank you, Bianca. Thank you, Radu. Thank you to everyone who attended. You'll get a link to additional information and to the recording of this video in a thank you email. Well, that's it for us. Have a nice afternoon and hopefully see you next week.